Question 4, we're looking at an electromagnet. A relay is an electrically operated switch. The electric circuit shown below uses the relay to switch on a light bulb. The relay has a coil containing a sliding iron core to turn on the light bulb. So let's look, we've got a light bulb here, and we've got a circuit with a power supply there, and this part over here, this is the power supply for the coil of wire, and when it's switched on, presumably a magnetic field will pull this edge that way to contact these edges here and complete the circuit so that the light bulb will go and current can flow around it. That's actually getting into the answers to the question. But A says explain how the light bulb is turned on by the coil. Two main things. When the power supply in the coil, so that's right, coil power goes on, that leads to induced magnetic field in the coil. That magnetic field will attract the sliding iron core, pulling the contacts to the left, completing the circuit. That's the right hand side circuit. So you'd need to detail each of those steps. B, we have the power supply for the coil now turned on. In the diagram below, the direction is given of the current through the coil. On the diagram we are to use the letters N and S to mark north and south. Presumably N is for north and S is for south. That would make sense to mark those poles of the coil. And then we also have to draw the magnetic field pattern produced outside the coil. So not interested in inside, just outside the coil. Indicate the direction of the magnetic field with arrows, which is the convention. So how we're going to do this, we've got another right-hand rule. This one, under different names, this one's called the right-hand grip rule. For this one, your fingers give the current, and your thumb gives the direction of the B field. So in this case, we have our fingers doing the direction of the current. They're coming from the back and over to the front. Remember, it's the right hand, so how you would grip this is with your thumb pointed in this direction and your fingers coming up and over the top, from the back to the front. So your thumb is a consequence of the direction of the current flow through the loop, and that means in the direction there, remember it goes from north to south, this is the north end, and the other end has to be the south end. Okay, and that's part one. Part two wants us to draw the magnetic field lines outside, so going from north to south. So we'd have something like this with arrows going from north to south. We would have that on both sides, and we might have another loop expanding a little bit further out. Should be even, I haven't drawn it very well at this end, but you get the idea. And depending on the strength of it, those lines will be closer or further apart. We don't know, so we're just illustrating here. And there might be a few lines sort of escaping out like this. So we still draw arrows on those pointing away from the north end. Same thing here with the south end pointing into the south end. So that clearly gives us the arrows. Okay. This is part C. Describe two modifications that can be made to increase the strength of the magnetic field produced by the coil. Okay, well, the magnetic field is proportional to the current running through, so if you increased the current, that would work. Double the current, double the field, something like that. There's actually three ways you could do this. You can add an iron core, because iron will magnetize inside that magnetic field and will help focus the magnetic field, meaning the field lines are closer together and it becomes stronger. And the third way, which you're not given, room to write, or depends which, 2 or the 3 would be fine, is to increase the number of loops in the coil. So you want to make that increase, because remember each loop in the coil has one part of has its own little magnetic field around it. As soon as you add a next one, it sort of adds to it and it doubles, and another loop, and it makes it stronger and stronger and stronger and stronger and stronger the more loops that you have. So those are 3 ways you could do it. D. The circuit in a factory contains 4 relay switches. This is going to be a slightly longer and trickier question, just so you know. So 4 relay switches is shown in the diagram. Here's our diagram. The relay switches are wired in parallel to a 65 volt power supply. Each relay has a power consumption of 35 watts. So we now need to calculate the combined resistance of the relay switches. Tricky. Now, if we knew the resistance of each individual one, since they're all the same, we can calculate that using our information we have, then we would add them up as resistors adding in parallel. That's one way to do it. We could also look at the total. Can we do it that way? Have we got enough information? We have the power of each relay is 35 watts, and we would times it by 4 to get the total, which would be what's that? 140 watts. That's if we're dealing with the total. So, but for each individual we have the power there, and the voltage is going to be 65 volts for each individual and for the total. It's the same. So we could work out using the power formula, P equals I times V, and then since we have Ohm's law as I equals V over R, we could substitute this part into here in place of the I, which would give us V times V over R, which is V squared over R. Let's just get rid of that. So we could work out the resistance. Since we have the voltage and the power, we could work out the resistance of each individual one of those excuse me, relays, and then we can add them up using the resistance formula. Alternatively, that's resistance in parallel. Alternatively, we can just take the total power and substitute that in here instead, and that should give us the total resistance. So I think that's probably the quickest way. So let's do that. So that's going to be our power. Our voltage, which is squared, is going to be from the 65 volts there, and we need to rearrange this formula, so we'll get R equals V squared over P, which will be the other way you could do it is by actually performing the calculation for the current and then substituting the current in, but I'm using this new formula that we've come up with from combining Ohm's law. So either way is fine and acceptable. They both show the same thinking. So anyway, 65 squared divided by the total power is 140 watts, and that'll give us the combined resistance, because remember it's dealing with the totals, of 30 ohms. And there you have it.